This skill is going to be exactly like the previous skill, except we're just going to have slightly more complicated questions. So in this question, we're trying to find the enthalpy change for the following reaction. So we've got 4NO plus 6H2O goes to 4NH3 plus 5O2. So let's start out by just writing out our reactants and products. So our reactants, we have NO gas and we have H2O gas. For our products, we have NH3 gas and we have O2 gas. Okay, so we need to go ahead and look at the three reactions provided in the table. We need to figure out the direction they need to be in order to get the reactants and products on the right sides, and how many moles of each of them we need, so that when we combine all of the reactions, we end up getting the goal reaction shown at the top. So let's start out by identifying where our reactants appear in these equations. So first let's look at NO. NO appears here, and that's the only place that it appears. So since we know NO is a reactant, it has to be on the left. That means this equation is already in the right direction. So we can choose forwards for this equation here, because we know NO needs to be a reactant. Our other reactant is H2O. Let's find that. Here's H2O. Currently in reaction 3, that's in the products, but we know it needs to be in the left-hand side on the reactants. So that tells us we're going to have reaction 3 backwards in order to have that in the correct place. Now let's look at our products. One of our products is NH3. We can see NH3 here. That's currently in the reactants of reaction 2, but we need it to be in the products eventually on the right-hand side. So that's telling us reaction 2 is going to have to be backwards. Lastly, we have O2. We can see O2 actually appears in multiple places here. It appears here and it appears here. So we know we need to have O2 on the right-hand side in the products eventually. Since it appears twice, it could be in the reactants for one and the products for another, so long as we end up with more in the products so that overall we have it in the products at the end. But right now we can see for reaction 1, the O2 is already in the products, and that's a forwards direction, so that's good. And for reaction 3, the O2 is in the reactants, but we already know that's a backwards direction equation, so that's going to end up in the products anyway. Awesome, so we figured out our directions. Let's go ahead and write out our equations now, but using the direction that we've decided. So reaction 1, it's forward, so that's just going to look the same. So we've got 2NO gas goes to N2 gas plus O2 gas. For reaction 2, we've decided that has to be backwards, so we're going to put the products first. So we've got N2 gas plus 3H2 gas goes to the reactants, which is 2NH3 gas. And then for reaction 3, again, this is backwards. So we're going to need to put the products first. So we've got 2H2O gas gives us 2H2 gas plus O2 gas. Okay, so those are our three equations written out now in the direction that is required. Now we need to figure out how many moles of each equation we need. So we know that nitrogen monoxide, NO, only appears in this equation. And we know from our goal equation, we need 4 of them. Right now we only have 2. So we're going to have to multiply this whole equation by 2 so that we can end up with 4 nitrogen monoxides in our reactants. So I know I'm going to need 2 moles of that. In reaction 2, this is where we're producing NH3 ammonia. That's the only place NH3 appears in any of our 3 equations that we're using. In our goal equation, we have 4 ammonias, 4 NH3. So we must need 4 here as well. So currently we have 2. So again, we're going to have to multiply that whole reaction by 2. So we end up with 4 NH3s. And then lastly, in our third equation, H2O appears there. That's the only place it appears in our 3 equations. We know that we are going to need 6 H2Os because that's what our coefficient is in the goal equation. Currently, we have 2 H2Os in this reaction. So we're going to need 3 sets of that. So we end up with 6. So 2 of this and 3 of this. Okay, let's go ahead and write out our whole equation with all these things added together to make sure that that works out. So we've got 2 sets of 2NO gas, which is 4NO gas. From reaction 2 in the reactants, we've got 2 sets of N2 gas plus 6 sets of H2 gas. And then in the reactants for our third reaction, we've got 3 sets of 2 H2O. So 6 H2O gas. Then in our products, for the first reaction, we've got 2 sets of N2 gas and 2 sets of O2 gas. From the second reaction, we've got 2 sets of 2 NH3. So that's a total of 4 NH3 gas. And then finally, from our third equation, we've got 3 sets of 2H2. So that's 6H2 gas and 3 sets of O2. So that's 3 O2 gas. Okay, so now we need to see if there's anything that needs to be cancelled out. So on our left-hand side, we can see we've got 2 N2s here. We also have 2 N2s here on the right-hand side. So those are going to cancel out. We can also see we've got 6 H2s here and 6 H2s here. That appears on the left and the right in both the reactants and the products. So again, that will get cancelled out. And then we can also see on the right-hand side, we've got 2 O2 and we've got 3 O2. So those can be combined together to make 5 O2. So that leaves us overall with 4 NO gas plus 6 H2O gas goes to 5 O2 gas plus 4 NH3 gas. That's our overall equation we found by adding together 2 sets of reaction 1 forwards, 2 sets of reaction 2 backwards, and 3 sets of reaction 3 backwards. And that matches exactly with our goal equation. We can see we've got 5 O2s there and 5 O2s in our result. So we've successfully figured out how to combine those 3 reactions to form our goal equation. Now we're ready to go ahead and find our enthalpy change of reaction. Again, we're going to use the Hess's law equation to do that. So let's go to our reference sheet. Here's Hess's law. The enthalpy change of reaction is equal to the sum of the enthalpy change of reaction of the steps. So to find out enthalpy change of reaction, we're going to add up the enthalpy of reaction of the steps, but we need to make sure they're in the right direction. If it's backwards, we're going to have to make them negative. And we need to make sure we've got the right number of moles. So we're going to multiply the enthalpy of reaction by the number of moles required. So that's going to get us, for reaction 1, it's forward, so it's going to be positive. We need 2 sets of it, and the enthalpy of reaction is negative 181. Then for step 2, this one's backwards. So we're going to need to have a negative sign. We need 2 sets of it, and the enthalpy change is 92. And then for reaction 3, again, it's backwards, so we need a negative sign. We've got 3 sets of it, and the enthalpy of reaction is negative 484. So we're going to need to put all of that into our calculator. That's going to get us an overall enthalpy change of reaction of 906 kilojoules per mole. So we can fill that in here. And again, since we've got a positive number, that means we are absorbing energy, which means this is an endothermic reaction. So as you can see, this works exactly the same as the previous skill. We're looking at our reactants and products in our goal equation. We're going to identify where they are in our three reactions that we're provided with in order to figure out, do we need those reactions to be forwards or backwards? Then we're going to look at how many of each reactant and product we have in our goal equation and use that to figure out how many moles of each of the three reactions we need. We'll add those reactions all together with the right number of moles and direction to find overall our goal reaction. Then we're going to use Hess's law to add up the enthalpy change of reaction for all of our steps. Remember, if it's backwards, we're going to make it negative, and we're going to multiply by the number of moles required for each of those reactions. We'll add those all together to get our overall enthalpy change of reaction.